Okay, so we're going to go over the general multiplication rule, and we're going to go over some examples of how you make some tree diagrams with probability. Okay, so the general multiplication rule says that the probability that events A and B both occur can be found with this rule. So probability of A and B, remember the probability of A and B is like the same as using this intersection symbol, so upside down U. So probability of A intersect B will be equal to the probability of A times the probability of B given that A has occurred. So remember that this is a conditional probability. And this is the conditional probability of B because we're saying that what's the probability of B given that A has occurred. Now, sometimes this won't be any different than just the probability of B, but you always want to be aware of that because sometimes it could change. So as usual, let's go through an example so we can make much more sense of this. Okay, so here we got playing in the NCAA. So about 55% of high school students participate in a school athletic team at some level. And about 5% of them, 5% of these athletes go on to play on a college team in the NCAA. So now the question is, what percent of high school students play in a sport in high school and go on to play a sport in the NCAA? Okay, just for the purposes of using that formal equation, let's have two events A and B, and let's have A be that they played in high school. That they played in high school. A student played in high school, and B being that they're playing in college. Okay, so we're finding the probability then of A and B, because it's saying play a sport in high school and play a sport in college, or play a sport in NCAA. Probability of A and B. And remember, we found that to be the probability of A times the probability of A, times the probability of B, given that A has occurred. So the probability of A and B is equal to the probability of A times the probability of B, given that A has occurred. Now why is this necessary? Because in this case, we're only gonna focus on the students that already played a sport in high school, because it's saying what percent of high school students that played a sport, what percent of high school students that played a sport in high school go on to play a sport in NCAA. So you have a condition. The condition is that they played a sport in high school, and that's what that is. So A is to put the probability they played in high school, 0.55. What's the probability that they're going to play in the NCAA given that they play in high school? And it says about 5% of them go on to play on a college team. So 0.05. So 0.05 times 0.55. So 0.0275 we get. So then in general, we have that 2.75% of all high school students will go on to play a sport in the NCAA. Okay, so let's look at this tree diagram example. Okay, so here we have late for school. Shannon hits the snooze bar on her alarm clock on 60% of these school days. She doesn't hit the snooze bar. There's a 0.9 probability that she makes it to class on time. However, if she hits the snooze bar, there's a 0.7 probability that she makes the class on time. So it changes, as you can see. When she snoozes, she has a lower chance of making the class on time, as you would expect. So we're going to make a tree diagram to represent this situation, and then we're going to figure out what the probability on a randomly chosen day that Shannon will be late to class on. And then we're going to answer part C. As you hit that, what's the probability she hits the snooze bar, given that she is late for school? Anyway, so part A, let's focus on this tree diagram. So let's figure out what we're dealing with. So what we're dealing with is that she's either going to hit the snooze bar or she doesn't hit the snooze bar. That's how the day is going to start. Like she hits a snooze bar. So we say snooze bar. You can say no snooze, I guess. We'll just say no snooze for short. Hits the snooze bar, doesn't hit the snooze bar. And then the other thing that could occur after that is that she makes it on time to school, or she doesn't make it on time, she's late. Right? So she hits the snooze or doesn't hit the snooze, and she's either gonna be on time or she's gonna be late. So we start from here. We're starting with that. She's hitting the snooze bar. So let's go over here and actually write this like this. Our first branch, snooze bar, doesn't hit the snooze bar. Now, if she takes this branch, it's still possible that she could be late. You know, she could be on time or she could be late in both situations. So snooze bar, on time, snooze bar, late, no snooze, on time, no snooze, late. So we have like essentially 4 possibilities that's going on here. So in other words, if she takes this path, this is basically you're going to end up with the probability that she hits a snooze bar and it is on time. Probability of a snooze bar and on time. So probability S and T. Here it's a probability of hitting a snooze bar and being late. Here we got the probability that she is not going to hit the snooze bar and she's on time. And the probability that she doesn't hit the snooze bar and is late. So no snooze and is late. So when I set up my tree diagrams and try to figure out all these probabilities, that's really going to help you figure out all the answers to the problems even before you even know what the questions are, because this allows you to pretty much figure out everything if it's done right, obviously. So now on the corresponding branches, you put the probabilities. So we're told that she hits a snooze bar on 60% of the days. So on this branch, we're going to put 0.6. Now, if she hits the snooze bar on 60% of the days, that means she doesn't hit the snooze bar on 40% of the days. The 0.4 is there because either she hits the snooze bar or she doesn't hit the snooze bar, and those have to add up to 1. Now, we're told if she doesn't hit the snooze bar, there's a 0.9 probability she makes it to class on time. So if she doesn't hit the snooze bar, we're talking about no snooze on time. So on this branch, we'll go 0.9. But that means there's still a 0.1 chance of her being late even when she doesn't hit the snooze bar, because these have to add up to 1. Now, if she hits the snooze bar, there's a 0.7 probability she makes the class on time. So hits the snooze bar and is on time, that's 0.7. That means this will then be 0.3 because those have to add up to 1 again. And so then to find this probability, the probability she hits the snooze bar and is on time, you just do 0.6 times 0.7. And we get 0.42. To find the probability she hits the snooze bar and is late, you just do 0.6 times 0.3. And you get 0.18. Now, to find the probability that she doesn't hit the snooze bar and is on time, you do 0.4 then times 0.9. And we'll get 0.36. And last one, find the probability she doesn't hit the snooze bar and is late. You do 0.4 times 0.1. So there's the multiplication rule in action. Now that we got our tree diagram done, now we can answer these questions. So on a randomly chosen day, what's the probability that she's late for class? Okay, well, let's look at where and when she's late for class. So let's just, in general, we're just trying to find the probability. It's pencil. Probability of being late. Probability of L. Now, there's a couple different ways she can be late. She can be late by hitting the snooze, which is this, or she can be late by not hitting the snooze. There's two ways. So the probability of her being late would just be these two combined probabilities, because these four values tell you all the possibilities that can happen, all the possible outcomes. So the probability of her being late would be 0.18 plus 0.04. Which will then just be 0.22. Now, as a side note, and as a good tip for you when you're making these diagrams, make sure these final probabilities at the end of the branches add up to 1. Because again, it has, remember, the sum of all the possible outcomes in the sample space has to add up to 1. Otherwise, there's something wrong with your model. So 0.42 plus 0.18, 0.6, 0.96, or 1.0. So then this, you were good. Remember, it has to make sense. That also helps you figure out if you got your tree diagram is most likely done right. Okay, now part C. Suppose she's late for school. What's the probability she hit the snooze bar that morning? Okay, so here we got the probability, a conditional probability. The probability that, what's the probability she hit the snooze given that she's late? I'm giving up with this pencil. Probability if she hit the snooze given that she's late. Because remember, suppose that she's late for school. She's late for school, so that's our condition. The probability of S given L, that'll be the probability of them both occurring, the probability of S and L, over the probability of L. And the probability of A and B, or the probability of A given B is the probability of A given B over the probability of B. And so now that we see that we made this whole diagram, we can find our values on here. The probability of S and L, which is 0.18, divided by the probability of L, which we found already to be 0.22. We get like 0.8 or something. Yeah, we get 0.81 repeating. And there you have it.